A very good evening, students. Hope you had great holidays with family last week. Yeah, we should have such breaks in between. You know what, in UK countries and European countries, every 6 weeks, students get break of 1 week. It's very good, no? Okay, fine. Let's discuss the remaining topics of the second unit so that we can start the core of the heart of this subject, that is convolutional neural network, in third unit. So now some topics are left in second unit. We discussed various architectures of deep learning models, and activation functions and hyperparameter tuning is a part of second unit, but we discussed these two topics in first unit. Then supervised and unsupervised learning also we discussed during the discussion of first unit. And now we are discussing how to improve the performance of neural network. So there are several terms and terminology is associated, like bias and variance, then normalization, early stopping, dropout, pruning. These are the various ways using which we can improve the performance of deep neural network. So among these various ways, we discussed bias and variance last week, right? And at last, we discussed these four possibilities with two values of bias, like low and high, and variance. What if the variance is low, and what if the variance is high? So with this two parameters, four combinations are possible: low variance, low variance, high variance, and low bias, bias. So here you can see these four combinations, right? So I simply revise this quickly because you should remember that what was, like, you need to recall that what was discussed in last class. So, but if we will discuss these four possibilities, you will recall everything. Low bias, low variance. The combination of low bias and low variance, it shows an ideal machine learning model. Both should be low. Low bias should be low and variance should also be low. However, practically it is impossible, like for most of the application, it is impossible to achieve this, right? Second, low bias, high variance. With low bias and high variance, model predictions are inconsistent and accurate on average. So they are not so accurate, but like they are accurate on average. But this case occurs when deep learning model learns with a large number of parameters, and this leads to such condition when the bias is low and the variance is high, it leads to overfitting. We also discussed about overfitting during the discussion of first unit, but now I hope it is more clear that when learning parameters are more. We are going to discuss one topic related to this, like how we can reduce the learning parameters, and that is pruning, which is the last topic of this unit. Okay, so this case occurs, low bias and high variance. It occurs when deep learning model learns with a large number of parameters. They are called learning parameters, training parameters. And this situation leads to overfitting. Overfitting and underfitting are not good for any model. So there are also ways that how they can be overcome. So we need to, like in this case, to reduce the overfitting, we need to reduce the variance. Similarly, in third case, to reduce the underfitting, we need to reduce the bias, because we know that low bias and low variance, they create the ideal model. So to have an ideal model, we should have low bias. So in the third case, like if a bias is high, underfitting occurs, and to reduce that, there are ways. Okay, so third case is high bias, low variance. That is, with high bias and low variance, predictions are consistent, but like you can see that in second case the predictions are inconsistent but accurate on average. In this case it is reverse of that. You can see that predictions are consistent but inaccurate on average. These predictions are inaccurate on average. So this case occurs, of course, because high bias. So predictions are inaccurate, right? And in the second case, low bias. So predictions would be accurate on average. but they are inconsistent due to high variance. Okay, so we are discussing third case, high bias, low variance, predictions are consistent but inaccurate on average. And this case occurs when a model does not learn well with the training data set, or when it uses few number of parameters. See this, there in second case, it is using high number of parameters, while here it is using low number of parameters. So this points also describe the differences between overfitting and underfitting. So I hope you also understand the differences between overfitting and underfitting. Suppose if it is asked that what are the differences between this, then you should be able to describe that overfitting occurs when model learns from a huge, like large number of parameters. Underfitting occurs when model learns from a small number of parameters, data set, or uses a few number of the parameters. And moreover, like when there is underfitting, the bias is high and variance is low. When it is overfitting, uh, variance is high and bias is low. And the fourth possibility, high bias, high variance. Okay, now here this parameters doesn't mean only learning parameters. They also include the features of data set given for the model. Like, because in that data set also, like how many features are there, how many we can say variables are there. So we will discuss it again with the remaining terminology associated with this associated with how to improve the performance of deep learning models. Okay. The fourth is high bias and high variance. And with high bias and high variance, predictions are inconsistent and inaccurate. Both. You can see that. High variance means inconsistent predictions. So here we have in fourth possibility high variance, so inconsistent predictions. High bias, which is third possibility, high bias means inaccurate predictions. So in fourth, we have high bias. So inaccurate predictions, right? So high bias, high variance means inaccurate predictions and inconsistent predictions. Okay. Fine. So this was discussed in last class at last. Okay. Now the next topic as per your syllabus in second unit is discriminative analysis. This discriminative analysis, it is like popularly known as linear discriminant analysis, or it is also known as normal discriminant analysis, or it is also known as discriminant function analysis, right? So this is not new. This is known since many years. And let me tell you what exactly it is. Okay. This discriminant analysis, like it is used mainly for multi-class classification, because we have several methods for binary classification, but some of the models, some of the algorithms available for binary classification, they have some limitations, and to overcome them, we use this discriminant analysis. Okay. This discriminant analysis is a supervised learning algorithm, we can say, which is used for classification tasks in machine learning, and like machine learning or deep learning. And it is a technique which is used to find a linear combination of features. It is used to find, and that's why it is known as linear discriminant analysis. It is a technique used to find linear combination of features. Features means associated with data, features are there, right? So it is used to find linear combination of features that best separates the classes in a data set. In your data set, like data may belong to two classes, data may belong to three classes, data may belong to multiple classes. If data in your data set belong to two classes, we call it binary classification problem. If it belongs to, like data in data set belong to more than two classes, we call it multi-class classification problem, right? So the job of this LDA is, it is used to find a linear combination of features that best separates the classes in a data set. So that is the main purpose of this. And in other words, we say that it is a dimensionality reduction technique. It is a dimensionality reduction technique. Okay, so what exactly dimensionality reduction means? I'll tell you again on next slide, but let me tell you what exactly it is. It is a pre-processing step. Dimensionality reduction is a pre-processing step in data science pipeline, or you can say in machine learning projects. It is a pre-processing step for applications of pattern classification. And the goal of this linear discriminant analysis is to project the features in higher dimensional space onto a lower dimensional space. To project, like, please imagine that suppose there is a multi-dimensional space. We know that if there are two axes, x and y, it is two-dimensional space. If there are x, y, and z axis, it is three-dimensional space, right? So like this LDA, it is used to project the features in higher dimensional space into a lower dimensional space, maybe from 3 to 2, 2 to 1, two-dimensional to 1, or three-dimensional to 2. Three-dimensional means x, y, z axes are there. So if we project features from x, y, z axis into lower dimensional, say 2D, that is xy, then it is like conversion, like from higher dimensional to lower dimensional. So this linear discriminant analysis, it is used to project the features in higher dimensional space into a lower dimensional space. This is to avoid the curse of dimensionality and also to reduce resources and dimensional cost. So why we want to project from higher dimensional to lower dimensional? The reason is that to avoid the curse of dimensionality and to reduce the resources and dimensional cost. Okay, so in many applications, this need arises and we use this LDA. Okay, the original technique was actually this original technique LDA, it was developed in 1936. So see, it is like almost 90 years, right? So the technique was developed in the year 1936 by Ronald Fisher, and it was named linear discriminant or Fisher's discriminant analysis. That time it was known as Fisher's discriminant analysis. Okay, Ronald Fisher. The original linear discriminant was described as a two-class technique. The multi-class version was later generalized by C.R. Rao, you know this mathematician, as multiple discriminant analysis, and they are all simply referred to as the linear, like whether it is whether it is for two-dimensional two-class technique or whether it is multiple discriminant analysis, they all are now known as linear discriminant analysis. Right. Okay, so here I have included one example. Let me tell you what this example tells. For example, suppose we have two classes in data set and we need to separate them efficiently. Okay, in given data set, there are two classes and we want to separate them efficiently. Now, classes can have multiple features. Classes can have multiple features. Okay. Using only a single feature to classify them, to classify the records in data set may result in some overlapping. I hope you are getting this point. We are given a data set. Data set has multiple records. We want to separate these records in two classes because this data in data set represent two classes. Okay. Now this data, multiple features are there, multiple columns are there. For example, for student data, we have marks of different subjects, we have percentage, we have a score in co-curricular activities and so on. We want to classify them in two classes, above average and below average students based on these parameters, that percentage, marks in percentage or marks, total marks, participation in co-curricular activities and blah, blah, blah. So many features are there. Okay. So multiple features are there. Now, instead of using all those multiple features to divide students into classes above average and below average, we are using a single feature. Let's say we are using only marks, or let's say we are using only score in co-curricular co-curricular activities. So if we use single feature to classify the students in two classes, the result may be overlapped. Classic, like, okay, so this may like this figure shows that how the data in two classes may overlap. So we will keep on increasing the number of features for proper classification. There may be 5 features in your student data set. So first, for example, we were classifying considering only total marks, but then we can increase one more feature. We can increase the score of co-curricular activities. So we can, like, we keep on increasing the number of features for proper classification. Dimensionality reduction is used here in areas like image recognition, predictive analysis in marketing, and so on, right? So this is just an example. So what exactly the dimensionality reduction? We have already discussed briefly that what it is. Techniques of dimensionality reductions are important in applications of machine learning, data mining, bioinformatics, information retrieval. In all these areas, this dimensionality reduction is required. And the main agenda of dimensionality reduction is to remove the redundant and dependent features. To remove the redundant and dependent features. Let me give you one example. Suppose your student database includes 4 columns like marks in subject S1, marks in subject S2, marks in subject S3, and total marks. I repeat, marks in subject S1, marks in subject S2, marks in subject S3, and total marks. Now, of course, total marks, consider the marks in S1, S2, and S3. So instead of considering all these 4 columns, all these 4 features, I can consider only total marks because it includes the marks of S1, S2, and S3. So this is like redundant information. This is redundant information. I'm considering S1, S2, S3, and total marks also. So instead of that, I can consider only total marks. I can remove S1, S2, S3, marks of S1, S2, S3. Right? So the main agenda of this dimensionality reduction is to remove the redundant and dependent features by changing the data set onto a lower dimensional space. And in simple terms, they reduce the dimensions. They reduce the number of variables in data set in a particular data set, like while retaining the most of the data. Like core of the data should not be lost. Right? We have to maintain it. So it retains the most of the data, right? Only redundancy is removed from the data set. Okay. So that is dimensionality reduction. Okay. Okay, let me discuss the motivation for LDA, like why LDA should be used and when it should be used. Okay, fine. Okay, regarding dimensional reduction, okay, let us discuss it again when it comes. I wanted to tell you that multi-dimensional data comprises multiple features having correlation with one another, like correlation I explained. And you can plot multi-dimensional data in just 2 or 3 dimensions with dimensionality reduction because it allows the data to be presented in an explicit manner which can be easily understood by a layman. So, like, okay. Now, what are the limitations? Here I have included the limitations of logistic regression because those limitations motivated researchers to invent a new approach for multi-class classification. Logistic regression is a simple and powerful linear classification algorithm in machine learning, and it has some disadvantages which have led to alternate classification algorithm like linear discriminant analysis. Some of the limitations of this logistic regressions are this: two-class problem. Logistic regression is traditionally used for two-class and binary classification problem. Though logistic regression can be extrapolated and used in multi-class classification, this is rarely performed, though it can be extended. On the other hand, linear discriminant analysis is considered a better choice whenever multi-class classification is required, and in the case of binary classification, both logistic regression and this linear discriminant analysis are applied, right? So LDA is more suitable for multi-class classification. It can also be used for binary classification, though we already have logistic regression, which is performing good for binary classification. The next disadvantage of logistic regression is that it is unstable with well-separated classes. Logistic regression can lack stability when classes are well separated. And this is where LDA comes in, right? And unstable, it is also unstable with a few examples, like if there is a small amount of data. So if there are a few examples from which the parameters are to be estimated, if the data set is small, then logistic regression becomes unstable. So here also we can use linear discriminant analysis because it is a better option, as it tends to be stable even in such cases when we have a small amount of data. So this is the motivation for LDA. Okay, now let us discuss the practical approach to an LDA model, how exactly it works. Suppose we have two sets of data points. Okay. Suppose we have two sets of data points belonging to two different classes that we want to classify. Now, as you can see in this figure, when the data points are plotted on the 2D plane, there is no straight line that can separate the two classes of the data points completely. So in such cases, because you can look at this graph, right? You can try to put this dotted red line at different locations in this graph. You will not find any line which will separate two classes, data of two classes. One class is represented with green circles and second class is represented with black circles, right? So anywhere if you plot this line, it will not clearly separate the data in two classes. So in this case, LDA is used, which reduces to 2D graph. This is 2D graph, right? X and Y axes are there. So in this case, we can use LDA, which is used to reduce 2D graph into 1D graph in order to maximize the separability between the two classes, right? So here we can use this LDA. Okay, so how can we do this? When we use LDA to reduce the 2D space into 1D space, we have to follow this criteria. LDA uses both the axes here, X and Y, to create a new axis, and it projects data onto a new axis. It is a 2D, so definitely when we will project this into lower dimensional, it will be 1D. From two-dimensional space, we will project this data into one-dimensional space. Okay, so to create a new axis and projects data onto a new axis in a way to maximize the separation of these two categories, we will reduce like this 2D graph into 1D graph following this criteria. What is the criteria? Maximize the distance between means of the two classes and minimize the variation within each classes. Maximize the distance between means of the two classes and minimize the variation. Minimize the variation between the data within the same class and maximize the distance between the data in two classes. So following this, we have to project data from two-dimensional space to one-dimensional space. So here you can see like how we can do that. Okay. So now we want to generate a one axis. So in the second graph, you can see that it can be seen that a new axis in red in second graph, okay, is generated and plotted in 2D graph such that it maximizes the distance between the means of the two classes and maximizes the variation within each class. I hope you have learned mean, mode, median, right? So here we are using the mean value. Okay, now in simple terms, this newly generated axis increases the separation between the data points of the two classes. And after generating this new axis, using the criteria we have just discussed, all the data points of the classes are plotted on a new axis, and they are shown here in this figure. You see this, right? So they are now reduced to one axis. Fine. So, but linear discriminant analysis fails when the mean of the distributions are shared, as it becomes impossible for LDA to find a new axis that makes both the classes linearly separable. In such cases, we use non-linear discriminant analysis. Presently, we are discussing linear discriminant analysis. So when there is a problem, when mean of the distributions are shared, we have to use non-linear discriminant analysis. Right? So this is linear discriminant analysis. These are the extensions of linear discriminant analysis. 3 extensions are there: quadratic discriminant analysis, flexible discriminant analysis, and regularized discriminant analysis. Okay, so just for your information, I have included the extension. Quadratic discriminant analysis means each class uses its own estimate of variance. Flexible means where non-linear combinations of inputs are used, such as, it's okay if you do not because to have good information on these 3 extensions, you need to go in deep, right? So just like to make you familiar with this terms: quadratic discriminant analysis, flexible discriminant analysis, regularized discriminant analysis, I have included this contents. Otherwise, it's okay if you do not know much about this, right? These are the advantages and disadvantages of linear discriminant analysis. Advantages are, it is a simple and computationally efficient algorithm. It can work well even when the number of features is much larger than the number of training samples, right? Where logistic regression fails. So this can work. You see that then the number of training samples, training samples, matlab number of records may be less in the data set, but the number of variables, number of features, they are high in number. Okay, so this works well. This LDA works well when we have more number of features compared to number of records in data set. This can handle multi-collinearity, correlation between features in the data set. So that's why we discussed that it finds the correlation. And if it finds that other features are representing the redundant information, then they can be removed. But everything comes with pros and cons. So here are the disadvantages of this LDA. It assumes that data has Gaussian distribution, which may not always be the case. There are different distribution, this usually comes, this topic you learn usually in data science subject or machine learning subject, that which are the different types of data distributions. So Gaussian distribution, normal distribution, different types of normal distributions are there. So this method, this LDA method, it assumes that it has a data has a Gaussian distribution, but all the time data is not in Gaussian distribution, and that time LDA doesn't perform good. LDA assumes that the covariance matrix, again, this is a term related to statistics, term related to machine learning, term related to data science, right? But it's okay, to revise those concepts, or if you have not learned that subject, that's why the first 2 units are there in this subject, right? Because the the core of this subject, deep learning for computer vision, wherein you will study the convolutional neural network, that you will learning of that CNN, you will start from 3rd unit. So first 2 units are in fact revision of machine learning and important concepts related to data science and machine learning both, right? So this assumes that LDA assumes that covariance matrix of the different classes are equal, which may not be true for all data sets. It also assumes that the data is linearly separable. I told you that if data is not linearly separable, then we cannot apply this LDA. We have to use that non-linear discriminant analysis. So this linear discriminant analysis, it assumes that data is linearly separable, which may not be the case for all data sets, right? And this LDA may not perform well in high dimensional feature spaces. So these are the disadvantages of this linear discriminant analysis. But applications are many for this linear discriminant analysis. Here, some major application areas are included on the slide. This is used for face recognition. Face recognition is the popular application of computer vision where each face is represented as the combination of a number of pixel values. Where each face is represented as the combination of a number of pixel values. And in this case, LDA is used to minimize the number of features to a manageable number before going through the classification process. So LDA is useful for face recognition. This LDA here generates a new template in which each dimension consists of a linear combination of pixel values. And if a linear combination is generated using this LDA, then it is called linear, like Fisher's linear discriminant, then it is called Fisher's face. Okay, the next is in healthcare, in medical domain. In medical field, this linear discriminant analysis has a great application in classifying the patient's disease on the basis of various parameters of patient health and the medical treatment, which is ongoing. On such parameters, this LDA classifies disease as mild disease, moderate, or severe, right? What is the condition of disease? What is the status of disease? Mild, moderate, or severe. And this classification helps doctors in either increasing or decreasing the pace of the treatment. Okay. In customer identification, the next application area is like to identify the customer segment. Okay. So in customer identification, this LDA is currently being applied with the it has been applied. It can easily identify and select the features that can specify the group of customers. We also call this as customer segmentation, customer identification problem or customer segmentation problem, because we want to segment customers in different groups, right? So customers can be grouped in different segments using this LDA. So with LDA, we can easily identify and select the features. We identify as well as we select the features that can specify the group of customers who are likely to purchase a specific product in a shopping mall. So this can be like, this is not only used for shopping, it is also used in banking, like customer segment. Who are the customers who would like to have a personal loan or housing loan or say credit card, right? So we segment customers in different groups. So it may be for e-commerce domain, it may be for finance domain, or so on. This can be helpful when we want to identify a group of customers who mostly purchase a product in shopping mall or on e-commerce websites. Next application area is it is used for predictions. Yeah. So LDA can also be used for making predictions and in decision making. For example, will you buy this product will give a predicted result of either one or two possible classes as the buying or not. Okay. And in learning. So learning is required. For example, robots are being trained for learning and talking to simulate human behavior. or to simulate human work. And it can also be considered a classification problem, right? So in this case, LDA builds similar groups on the basis of different parameters, including uh, including pitches, frequencies, sound, tunes, etc. So these are like some of the application areas where LDA is used. Fine. Okay, now the next topic is batch normalization. Okay. Okay. So this is LDA is over. So I'll take questions related to LDA at the end of class only. Let us discuss batch normalization, because by next class, I want to complete the second unit so that we can start the main deep learning models related to computer vision. Like we can start the third unit, right? Okay, now let's discuss the batch normalization. Objectives of batch normalization are to learn how to improve the neural network with the process of batch normalization, and to understand the advantages of using batch normalization, or to understand the advantages batch normalization offers. So these are the objectives of learning batch normalization, that how it improves the neural network performance and what are the advantages of using it. Okay. One of the most common problems of data science professionals is to avoid overfitting. Or one of the most common problems of machine learning experts is to avoid the overfitting problem, right? You may use data science or machine learning. Please remember, I told you in first class that data science and this machine learning, deep learning, they go together. Without machine learning, data is not useful. And without data, machine learning has no significance. And that's why, though we learned this machine learning around 2000, in 1999, we never applied after learning this subject. We have started, like I have started applying it in last 1 decade. Because in last 1 decade, we have generated tons of digital data in real life sectors. And so it has been possible to apply this data analysis techniques, right? So machine learning techniques are not useful if you don't have data. And data, though you have digital data, that digital data is not useful if you don't have powerful machine learning techniques which analyze this data. So that's why I said that this overfitting problem, it is associated with data science also, it is associated with machine learning projects also. So have you come across a situation when your model is performing very well on the training data, but is unable to predict the test data accurately? This problem is called overfitting, right? We discussed this problem earlier, that what is overfitting problem? Your model, your trained model, the model which you are using, maybe machine learning or deep learning model, it is performing very well on the training data, right? Please remember that given data set is divided into training data set and testing data set, right? So your model is working very good for training data, but it is unable to predict the test data accurately. And this is called overfitting. The solution to such problem is regularization. The solution to such problem is regularization, and the regularization techniques help to improve a model and allows it to converge faster. So we have several regularization tools at our end, and some of they are early stopping, dropout, weight initialization techniques, and batch normalization. Please remember which are the regularization techniques. Early stopping, dropout. Early stopping, we are going to discuss after batch normalization. So early stopping, dropout, we discussed in first unit. So early stopping, dropout, weight initialization technique, batch normalization, these are the regularization tools. And the regularization helps in preventing the overfitting of the model, and the learning process becomes more efficient. Okay. So now let us explore one batch normalization. Okay, now before we discuss batch normalization, I have included the definition of normalization here. Not definition, but what is normalization? Because this is also very popular term used in data science, normalization. Okay, so let us first see what is normalization. Normalization is a data pre-processing tool which is used to bring the numerical data to a common scale without distorting its shape. So that is called normalization. Let me tell you, I give you one example. The example is, suppose there are two divisions in your college of computer engineering. Division 1 having intake 60, division 2 having intake 60. So both the division have intake 60. Okay. So now both the divisions, they are learning this subject, deep learning for computer vision, but two different teachers are teaching this subject in both the divisions. Now teacher in division 1 has taken exam out of 100 marks, and teacher in division 2 has taken exam out of 150 marks. Okay, same subject, deep learning for computer vision, but two different teachers, they have taken exam mid exam or mid semester exam. One has taken out of 100 marks and second has taken out of 150 marks. Now you want to check that among these two division, who is the outperforming, who is the who has scored the highest marks, right? So you want to identify that student who has scored highest marks among these two divisions. So you can't compare the marks out of 100 with the marks out of 150. So you need to convert the range. You need to convert the scale of this. So you have two options. Either you can use scaling. Scaling is different from normalization. Scaling means either you can scale up marks from 100 to 150, or you can scale down marks from 150 to 100. And now you can compare, because all the students, they have scored marks out of 100, and you can find who has scored highest marks among these two divisions. So this is called scaling. Normalization means you are converting marks out of 100 to some scale, let's say in range 0 to 1. It's a very small range, but you are converting marks 100 from 100 to 0 to 1. Similarly, from 150 also you are converting into 0 to 1. So you are bringing them to a normal range. Normal range. See, it is called normal range. We are not scaling up or we are not scaling down. We are converting marks into normal range, and then we are comparing, and that is called normalization. So normalization is a data pre-processing tool used to bring numerical data to a common scale. Common scale, you see, both are like 100 में से भी आपने 0 to 1 के बीच में ला रहे हो, और out of 150 भी जो marks है, you are bringing them down to 0 to 1 scale, range of 0 to 1. So this is like common scale without distorting its shape. And generally, when we input data to a machine or deep learning algorithm, we tend to change the values to a balanced scale. And the reason we normalize is partly to ensure that our model can generalize appropriately. अगर आप दो अलग रेंज से फीड करोगे मॉडल को, the bias में model may learn bias, right? So now okay, this is regarding the normalization. Now let's come back to our main topic, batch normalization. So what is batch normalization? It is a process to make neural network faster and more stable through adding extra layers in deep neural network. See, both are completely different, normalization and batch normalization. Both are different. Normalization kya hai? I explained you. Now I'm talking about the batch normalization. What is batch normalization? It is a process to make neural networks faster and more stable through adding extra layers in deep neural network. आपका जो deep neural network का architecture है, उसमें आप extra layers add करोगे. Okay, the new layer performs the standardizing and normalizing operations on the input of a layer coming from a previous layers. आपने जहां पे भी उन्हें ऐड किया है, so what they'll do, they will standardize and normalize the data coming from the previous layers. Okay, but what is the reason behind the term batch in batch normalization? So let me tell you what's the reason. A typical neural network is trained using a collected set of input data called batch. Similarly, the normalizing process in batch normalization takes place in batches, not as a single input. Okay, so let us understand with the help of this figure that how it occurs. Let us discuss this example. Suppose we have in this figure, you can see one deep neural network. Okay, so look at this deep neural network. It has L number of layers. So you can see that layers are W1, W2, W3, W4 up to WL. These are the layers of this deep neural network. Okay, bias is 0. And activation function uses sigmoid. Activation function used here is sigmoid. Okay. Okay. Now, initially our inputs to this neural network are represented as X1, X2, X3, and X4. They are the inputs. Okay. Now listen carefully. Our initial inputs X1, X2, X3, X4, they are normalized. Q, I don't know whether I discussed the data science pipeline or not in our initial classes, initial lectures. But if I have not discussed, then I tell you that what are the major 5 steps of data science pipeline. The first step is collect data, gather data. Second step is clean data. Second step is clean data. Third step is exploratory data analysis. So by the third step, we fine tune the data and we make data ready to fit to the neural network or to fit to the machine learning model, deep learning model. Fourth step is use machine learning, deep learning model. So here you fit the data. Okay. Model gets trained through this data. And the fifth step in your data science pipeline is interpretation, like deployment of, like interpretation of data, interpretation of classes generated by the model, interpretation of output generated by your trained model. So that is the fifth step. Okay. So by the third step, we complete the normalization. By the third step, we complete the normalization because we make data ready to fit to the network. So here, this is the neural network architecture, and X1, X2, X3, X4, they have come after. These are the data after exploratory data analysis. So they are already in normalized form. X1, X2, X3, X4, they are already in normalized form as they are coming from the pre-processing stage of the data science pipeline. Now, when the input passes through the first layer, you can see that when input passes first layer, which is the first layer? You can see the first layer. Okay, I have not highlighted in. It is the next slide. Okay. So when input passes through the first layer, it transforms as a sigmoid function applied over the dot product of the input and the weight matrix W. Similarly, this transformation will take place for the second layer and go till the last layer, as shown in this, as shown in the figure. Okay. Okay, fine. Now, although our input X was normalized although input to our this neural network is normalized, as it passes through layers, right? It was normalized, but with the time, output will no longer be on the same scale. As the data go through multiple layers of this neural network and L activation functions are applied, L activation functions are there because L layers are there. So this leads to an internal covariant shift in the data. Data does not remain in the same scale when you get output at the end. So the scale of the input data and the scale of the output data will vary at the end of one round. So here we need batch normalization. So how batch normalization work here? By now we are clear, like that why we need batch normalization. Why we need batch normalization? Batch means what? Like one one round. Batch normalization, why is it required? Because the scale of input data differs from the scale of output data. Why it differs? Because our input data passes through multiple layers, multiple activation functions, and that's why the scale becomes different. So let us see how batch normalization works. It is a two-step process. First, the input is normalized and later rescaling and offsetting is performed. Rescaling and offsetting is performed. Normalization is the process of transferring the data to have a mean zero and standard deviation. And then after that, offsetting is done. So these are the main two steps. I'm not discussing this two steps in detail because like those steps you may learn in data science that how exactly it works. But this is called batch normalization. And it is required because it helps us to improve the performance of deep neural network. How it is, why it is required? Because the range of input, the scale of input values differs from scale of output value at the end of each round. So we need to apply this batch normalization at the end of each batch. Fine. Okay, now before we proceed, before we discuss early stop mechanism, I would like to take your questions related to LDA and batch normalization. I can see that today, like most of the students are still in vacation mood and less number of students have joined. It's okay, but please tell them to join in next class because the terms which I am going to discuss in next class, early stop, dropout, pruning, they are very important for the deep neural network. And I'm sure that the third unit onwards, you are going to enjoy the classes the most because we are learning all this for understanding that convolutional neural network, which is very interesting model. Okay, you will really enjoy learning that model because that model is applied nowadays in most of the computer vision applications, and all the recent models like new models extensions of the CNN, they are also very interesting. Okay, so ask them to join from next class regularly so that they can understand all the terms associated with this deep neural network. But I would like to take your questions now related to these two topics.